Hello everyone. Now let's start our today topic: electric dipole in uniform electric field, or torque on a dipole in uniform electric field. So you know that torque that we have studied in the +1 class is torque. Torque means turning effect. What is torque? Turning effect on the dipole in uniform electric field. So what is uniform electric mean? That the region where the electric field magnitude remains same at every point, that is known as uniform electric field. So uniform electric field is represented by equispaced unidirectional parallel lines. This is the region of uniform electric field. Suppose we have here positive charge and here we have negative charge. So electric field lines are starting from positive charge and end at negative charge. So this is the region of a uniform electric field. Now in this uniform electric field we will place a dipole. This is a dipole having minus q charge and plus q charge A, B, and inclined in the uniform electric field with angle theta, making angle theta with the uniform electric field, and the dipole length is 2L. You know the dipole length is 2L. So you know that when any charge is placed in a uniform electric field, that will experience electrostatic force. So this plus q charge will experience the electrostatic force toward this negative charge. So this is the electrostatic force experienced by this negative charge F, that is equal to Q E. Similarly, this negative charge also experiences the electrostatic force but toward positive charge, that is equal to F2. Let us suppose this is F1, that is Q E. So force experienced by minus q charge is F Q E, and force experienced by plus q charge is Q E. So this is F2, this is F1. Sorry, F1. So these two forces are equal in magnitude, that is QE. This is also QE but opposite in direction. So here will take a negative sign. This negative sign indicate about the opposite direction. So here also will place a negative sign. So net force on the dipole is F1 minus F2, that is equal to QE minus QE is equal to 0. So this proves that when dipole is placed in uniform electric field, it will experience zero translatory force. This is very important, translatory force. We mean to say that when dipole is placed in uniform electric field, it will not execute any translatory motion. It will not execute any translatory motion, but it will execute rotatory motion. So you know that the cause of rotatory motion, that is equal to torque. Now we will here understand how the torque comes into play when the dipole is placed in uniform electric field. Now you see, here we have two equal forces, equal or unlike forces. Unlike forces mean they have different line of action. These are equal forces, but acting in opposite directions and having different line of action. You see, this is the line of action of this force, and this is the line of action of this force. So these two forces will form a torque on this dipole, and this dipole will try to rotate in this direction. This torque will rotate in clockwise direction and try to align in the direction of electric field. I think it's clear. So now two forces are equal in magnitude and opposite in direction and having different line of action. That is very important, different line of action. So forming torque on dipole, try to rotate clockwise and align in the direction of electric field. So because torque, that is denoted by the symbol tau, is equal to either force multiplied by perpendicular distance between two forces. So when we will drop a perpendicular on the line of action of this force here, Bn, draw Bn perpendicular on the line of action of force. So torque becomes equal to either force QE into perpendicular force between the two forces Bn. This is equation number 1. Now from triangle BAN, sin theta, that is equal to perpendicular upon hypotenuse, that is perpendicular is BN, and AB. So BN and AB, you know that 2L. So BN become is equal to 2L sin theta, equation number 2. Now using equation number 2 in equation number 1, we'll get tau is equal to QE into 2L sin theta. Now by arranging this equation Q, 2L E sin theta, and because P is equal to Q into 2L, so torque is equal to P E sin theta. This is the magnitude of the torque experienced by the dipole when it is placed in uniform electric field. Now because you know that the cross product of two vectors is represented by the sine of angle of theta. This is, so in vector form we can write torque P cross E vector. This is the torque in vector form. So you know that torque is a vector quantity whose magnitude, that is equal to P sin theta, and having direction. So direction we can find out by using right hand thumb rule. So direction of the torque is always perpendicular to the plane containing P and E. So in this diagram, the torque, the dipole is rotating in clockwise direction. So if we use right hand thumb rule, like in this way, right hand rule, so this is our thumb and this is our right hand, and we have to rotate the finger in the direction of the rotation of the dipole. So thumb is in downward direction. You see, thumb is in downward direction. So here direction of the torque is inward, that is downward. We can say that into the plane of a paper. I think it's clear to all of you. Torque is perpendicular to the plane containing P and E, and according to the right hand thumb rule, it is inward or into the plane of a paper. Now we'll start special cases of this expression. Those are very important exam point of view. Now special cases. The first one is when theta is equal to 0 degree. So firstly you understand what is theta. Theta is the angle, you see this theta. Theta is the angle between electric dipole moment and the direction of electric field. This theta is the angle between P and E. So when theta is equal to 0, then we can say that dipole moment is parallel to the electric field. Then we can represent it as, this is the uniform electric field, this is the uniform electric field, and here we have a dipole. This is what dipole minus Q, and this is plus Q, and this is dipole moment. The direction, you know that negative to positive, so direction is from negative to positive. So theta become here is equal to 0 degree. Then torque is equal to PE sine 0, and you know the sine 0 is 0, then torque becomes equal to 0. So here we have seen that the torque will not experience any torque, mean no turning effect. So this is stable position of dipole in uniform electric field, or stable equilibrium position. We can say that this is stable equilibrium position. Second case is when theta is equal to 180 degree. 180 degree mean the dipole moment is anti-parallel to E. We can represent it. This is the direction of uniform electric field, and this is what dipole. So here we will give negative charge and here positive charge. This is the direction of dipole moment. So theta becomes equal to 180 degree. Here we have negative charge. This is positive charge. So this is the direction of dipole moment. Theta is equal to 180 degree. Then again torque is equal to PE sine 180 degree. Sine 180 degree is equal to 0. Torque again is equal to 0. So here we have seen that when the theta is equal to 0 degree or 180 degree, torque in both the cases is equal to 0. This is stable position of the dipole in the uniform electric. Stable mean here positive charge, and here we have negative charge of electric field. Positive and negative, you know that attract each other. Here we have negative charge and positive charge of the electric field, they will attract each other. So we can say that this is the stable position. And here we have negative charge of electric field, positive charge of, here we have negative charge of electric field, and here positive charge of electric field. Negative repel each other, positive will repel each other. This is unstable position of dipole in uniform electric field. Here dipole will not experience any turning effect. It will not rotate but get repelled out of the electric field. It's very important. If we take third case, theta is equal to 90 degree. 90 degree mean the dipole is perpendicular to the direction of electric field. So here we have uniform electric field. This is the region of uniform electric field. Here we can say that positive electric field, negative of electric field here, and this is dipole. Here minus q charge, here plus q charge. The theta angle is 90 degree. So here torque is equal to PE sine 90 degree. Sine 90, you know that 1 that is equal to maximum torque. Here dipole will rotate. This positive, this positive, this negative will try to attract. This positive is not try to attract. So this dipole will rotate in this way and try to align in the direction of a uniform electric field and comes in a stable equilibrium position. Again, when theta is equal to 90 degree, mean dipole is perpendicular to direction of the electric field. So sin 90 that is equal to 1 maximum torque. It will experience maximum torque and dipole try to align in the direction of a electric field. This negative charge of the dipole is attracted by the positive of the electric field and this positive of the dipole is attracted by the negative of a electric field and try to align in the direction of electric field. So forming the stable equilibrium position. So I think this topic is clear to all of you. It's not very difficult, but you have to understand with open mind. So revise it properly. Thank you.